Today we'll be starting with the optics syllabus, and the first unit in your syllabus is the interference of light. So we'll be starting. This is the first lecture of the unit. So we'll be starting with coherence. What are coherent sources? What is interference? And Young's double slit experiment. So these topics we will be covering. So we start with the coherent sources. So, at first, we should have a definition of what are coherent sources and what is the criteria for the two sources to be coherent. The two sources can be coherent if the waves that are generated from the two sources have a constant phase difference, or they should be in the same phase. Rather, they should be in the same phase or they should have a constant phase difference. Here are the two waves. You can see that the phase of this wave is same as the phase of this wave. So these two waves have the same phase. And if there is a phase difference between the two waves, then that phase difference should be maintained. It should not change with time or the space. And the two waves should also be having the same frequency. So these are the two criteria. The one is the same phase or the constant phase difference, or the second is the same frequency. These two are the criteria for the two sources to be coherent. Practically, we don't have any two independent sources that are coherent existing. We don't have any existing two independent coherent sources. So what we do is we create two sources from a single source. And the most commonly used sources are the light emitted by the laser has the same frequency and phase, and the electrical signals from the sound waves travel with the same frequency and phase. Now we come to there are two kinds of coherences. One is a spatial coherence and the other one is temporal. Since we know that we move in two aspects, one is we move in the with respect to space, and the second aspect is that we move with respect to time. When the coherence is there with respect to space, this is called spatial coherence. When the coherence is maintained with respect to time, it is called temporal coherence. So, spatial coherence is concerned with the phase correlation of two different points across a wavefront at a given instant of time. At a particular time, we are examining the coherence of the two waves. The space can be different. It is related to position and it is also called transverse coherence. It is related to size of the light source, and the application is in the Young's double slit experiment. We will study it later on. And the second is the temporal coherence, which is concerned with the phase correlation of waves at a given point in the space at two different instants of time. So here the space is constant. The space is not changing, the time is changing. So it is related to time. It is also called longitudinal coherence. It is related to frequency bandwidth of the source, and this will be studied using Michelson interferometer. So let me revise. If I examine the two waves sitting here, that means the position is fixed. Time is varying. I examine the coherence just now and I examine it after half an hour. So the time has changed. And the coherence is maintained, so it will be a temporal coherence. Now if I measure a coherence at this position and simultaneously I measure coherence at a position 2 meters away or 3 meters away, whatever it will be. The time is the same, the space has changed, so it will be the spatial coherence. Now, since I talked that the spatial coherence is the coherence with respect to space and the temporal coherence is with respect to time. So the length at which the coherence is maintained in space is called coherence length, and the time duration that the coherence is maintained with respect to time is called a coherence time, which is denoted by tau. These are related by the simple velocity relation, distance upon time. Velocity L is the distance, tau is the time, and c is the velocity. This tau is a very small increment, so it is delta t. We denote it by delta t, which is equal to a small increment of the frequency, and frequency is inverse of time. We are using this relation, frequency is equal to velocity upon lambda, like v is equal to n lambda. We differentiate this and we get this. Just note at this quantity, C upon lambda square into del lambda. Del lambda by lambda is a quantity that we are concerned. We defined a factor, lambda upon T lambda, as a special purity factor. Now we consider the relation L is equal to C tau. Tau is equal to 1 upon del frequency, and putting the value of del nu from the previous relation, you get this, and putting the value of q, this equation reduces to lambda. This is the coherence length and corresponding coherence time in terms of the purity factor. So now what is interference? It is a process in which two or more waves of the same frequency, be it light, sound, or other electromagnetic waves, either reinforce or cancel each other, the amplitude of the resulting wave being equal to the sum of the amplitudes of the combining waves. So this is merely a superposition of the waves, but the waves should be coherent. The practical examples that you see in your daily life of the coherent sources are the soap bubbles, the bubbles on the surfaces, uh, this 7 colors Vibgyor on the compact discs. These are all due to interference of light. And what are the conditions under which we get interference? We have two major conditions, that the sources, the waves which are interfering, they should be coherent, and obviously the sources should also be coherent. If the waves are coherent, the sources will be coherent. And the sources must be monochromatic, that they must be emitting light of a single wavelength. If they are uh, emitting light of white light, like multiple wavelengths, then the corresponding wavelengths will interfere and will give their maximum. So the other requisites are, for a better picture, these two are the prime requirements for the interference. The others are the for a clear interference pattern. The amplitudes and intensities must be nearly equal to produce sufficient contrast between maxima and minima. The sources must be small enough that it can be considered a point source of light. The interfering sources must be near enough to produce white fringes. The source and its screen must be far enough to produce white fringes. The source must emit light in the same state of polarization. We can see these very dependencies when we calculate the path difference in the experiment to come. When we arrive at the formula for fringe width, then we will see these dependencies. Since I talked about interference with the monochromatic sources or with the coherent source, why can't light from a bulb be coherent? Since they emit radiations of a wide range of frequencies, including all the colors, and the light coming from the bulb is randomly generated in all directions. So the amplitude varies from a maximum to minimum in a particular direction because the direction is changing. Moreover, it is dependent on many factors, and we don't know where the wave will start, at what position or what phase the wave will start. So basically, in these terms, the light coming from a bulb is incoherent, and so we can for incoherent lights we can't get the interference pattern. And the first experiment that was performed for interference was by Thomas Young. And what he did, he just put a pinhole in a sheet, and sunlight was allowed to pass through it. The spherical waves were emitted from this. He put another sheet. He created two pinholes here. By this, he meant to have two coherent sources, to generate two coherent sources from a single coherent source. These are the two independent spherical waves coming out from these two pinholes. And light from these two pinholes will interfere. And this is the region that they will interfere. This is the region of crossover that where they interfere, and we will get the interference pattern on this screen, which consists of a maxima and minima pattern, a series of maximas and minimas. This is a video that I copied from some site for an educational purposes to explain to you. Let me just reshow. So light from the bulb, from a source is coming. It passes through the first slit. Then we have two slits separated by a distance, which will be the coherent sources. And then now light will come from these two slits. They will be the two coherent sources. And since we have used slits rather than the pinhole which was used initially, we have the cylindrical waves here. So these are the wave pattern that will be formed. So basically this is the diagram. We have two independent sources. We have a screen. We want to calculate the intensity at a particular point on the screen, that is point P. Light ray from the first slit comes. This is S1P is light ray from the first slit. S2P is the light ray from the second pinhole rather here. This is the central maximum line. This small d is the distance between the two slits. Since this point C is the midway of the two pinholes, so the distance of one pinhole from this will be half of it. That is d by 2. X is the distance from this central maxima to the point. So if this x is the distance, so what will be this distance? This is the straight line S1E. The distance EP will be x minus d by 2. And similarly, we have a straight line S2F. The distance FP will be x plus d by 2. So let's discuss this. We have the S1 and S2 as the closely spaced slits illuminated by a light of wavelength lambda. And if the two slits emit light in the same phase, then the superposition at the point C is constructive and it will be the central maxima. Now we need to calculate the path difference of the two waves coming from S1 and S2 at point P. The path difference will be S2P minus S1P. S1P is the path by this ray and S2P is the path traversed by this ray. So the path difference will be this path minus this smaller. So first we can consider this triangle PS2F. We apply Pythagoras theorem. S2P square is equal to capital D is the distance from this slits to the screen, capital D square plus x plus d by 2 whole square. So this distance is x plus d by 2, like I explained earlier. Similarly, for this triangle, it's S1p square is equal to d square. There is an error, I just noticed it. Otherwise, I would have rectified it. This should be x minus d by 2 whole square. This distance is x minus d by 2. It's wrongly here. It's x minus d by 2. We subtract this two equations. We get these. Open these to cancel out. Now we open these brackets. These two will be cancelled. This also will be cancelled. So we'll be left with 2xd. This is 2x. Now we expand the left hand side. We take this quantity to the down to the denominator. Now, since the distances are very small, these are very small as compared to this. So we can take them to be equal to d. We can also approximate S to be equal to d, and S1p is also equal to d. We substitute it here, so this denominator becomes 2d. 2 cancels out, so it reduces to xd upon capital. This is the path difference. So when this path difference is equal to an even multiple of lambda, then the interference will be constructive and we get a maximum. Maximum means a bright fringe. And when this path difference will be equal to an odd multiple of lambda, then it will be dark in fringes or minimas. Minimas means that the waves are out of phase and they are cancelling. The resultant intensity is zero. Maximum means they are interfering constructively and there is a maximum intensity. So we get a maxima minima pattern here. When two waves are in the same phase, the interference is constructive and the intensity is minimum, thereby producing a bright fringe. And when the waves are in opposite phase, the interference is destructive and the intensity is minimum or zero, and we get a dark fringe. These are the. In case of water waves, we have two slits, and these are the waves coming out on the water surface, and you can see the interference, the points of maximum and minimum displacements. Now we come to the intensity distribution. And if the two beams of light arrive at a point on the screen exactly out of phase, they will interfere destructively and the resultant intensity will be zero. But you may ask what becomes of the energy of the two beams, since the law of conservation of energy tells us that energy cannot be created, not be destroyed. So where the energy of these dark bands go? So the answer to this question is that the energy which apparently disappears at the minima actually is still present at the maxima. It is transferred from the minima to the maxima, where the intensity is greater than would be produced by the two beams acting separately. So the energy has been transferred from the region of minimum, from the minima to the maxima. In other words, it is not destroyed. And the average intensity on the screen is exactly that which have been in absence of interference. Like you can see, if there are two coherent sources, the intensity is maximum. In two intercoherent sources, it is a minimum intensity. Like intensity we know is equal to 2a square for a particular source. And when the intensity is transferred from minima to maxima, this intensity is doubled. The intensity of the maxima is doubled, which becomes 4a square, because the intensity of the minima will be 0. So average is still 4a is still 2a square. This is the average. For maxima, the intensity is 4a square and the minima is 0. So we end the topic here today, and we will resume with the other topics of the unit interference in our next class. I thank you all for your patient listening, and you can post your doubts on the chat of this video, and please subscribe and put your comments for the video. Thanks.